Hey folks, all right, welcome back. We're going to talk more about universal gravitation. And in this video, we're going to primarily do a couple examples and talk about the difference between the force of gravity and the acceleration of gravity. So I've rewritten Newton's law of gravitation. Oop, and I'm missing the r hat there. Okay. So again, the negative and the r hat. R hat simply means radial direction, in the direction of the radius. And the negative just means inward. Typically, you're not going to use either the negative or the r hat in any actual calculations you do. They're more to talk about the direction of this force. Now, as a reminder, all this means is that any two objects with mass attract each other. So let's say that these are our two masses here. Let's say we got a basketball and a marble. The marble will pull on the basketball, and the basketball will pull on the marble, and these two forces will indeed be equal and opposite according to Newton's third law. Okay. Now the two objects will, if let's say we were to put them in deep outer space away from any other forces, because obviously this force is really small. Like if you put a marble near a basketball, you don't see them pulling at each other, right? So this force is really small. But if you were to take these two objects and put them somewhere where there's no friction or anything and let them go and watch them long enough, they would eventually move toward each other and eventually hit each other. Their accelerations would be different. The basketball would accelerate much more slowly than the marble because even though the force acting on them is identical, okay, their accelerations are going to be different because their masses are different, okay? Now, as far as doing calculations go, and I gave you the value for big G. Big G was 6.67 times 10 to the negative 11th. And that's a constant of nature. It doesn't change. So in your equation, whenever you see a big G, it's always that number, okay? Now, as far as calculations go, I'm not going to insult your intelligence by giving you two masses and say plug into the equation and find a force. So we're going to do more fun stuff than that. I will make one more note on this equation, though. What's the radius? Okay, so here's what radius means. It means from the center of mass of one object to the center of mass of the other. So like in this picture here, this would be your radius. That's going to be important as we talk about things like orbit around the Earth and so on. So we're looking at from center of one mass to the center of the other. All right, so here's my first example. Let's say we're going to have three objects in this example. Let's say we got ourselves the sun, and let's say we got ourselves the Earth, okay? And for now, for the sake of argument, let's just pretend the Earth is stationary, which we know it's not, but let's pretend it is. And let's say you were launching a spacecraft toward the sun from the Earth, okay? So when the spacecraft is really close to Earth, the Earth will pull on the spacecraft more than the sun will. When the ship is closer to the sun will pull on the craft more than the Earth will. Well, there's some point in between there where the pull from the sun, so this is the force of the sun on the craft, will equal the force of the Earth on the craft, okay? So where is that? Well, first of all, we need some data. We need to know how far away the sun is from the Earth. Now, by the way, when we write this distance down, when they give you distances from one object to another, unless otherwise stated, it's center to center, okay? Now, if you're in class, you're going to get a data chart, okay? And on that data chart, it's going to talk about the sun is one of the things we talk about. And it says it's 149.6 million, or we'll just round to 150 million kilometers, okay? But here's what I'm going to do. I'm going to call that 1, okay? And matter of fact, that has a name. It's called 1 AU, and AU is short for astronomical unit. And it's defined as, 1 AU is defined as the average distance from the Earth to the sun, okay? So astronomers like to use bigger units than meters and kilometers and miles. So now we're going to talk about AUs, astronomical units, okay? But I'll write down on here that's approximately equal to 150 million kilometers, okay? So that'd be 150 billion meters, okay? Now, the other thing we need to know is the masses, okay? So for reference for later on, I will write the following. The mass of the Earth is approximately 5.97 times 10 to the 24th kilograms. And by the way, I'll mention how on Earth we know that, okay? We can't weigh the Earth, right? The radius of the Earth, which we're not going to need here, but we will need in subsequent problems, is approximately 6.38 times 10 to the 6th meters, or a little over 6 million meters, which is about 4,000 miles. Okay. So anyway, now, where is this place at? Well, the other data we need is the masses, or at least relative to each other. So here's the deal. The mass of the sun is approximately 330,000 times the mass of the Earth. So that's what I'm going to use. I'm going to use the Earth as 1, and the sun is 330,000. Okay. So this is 330,000 to 1. Now, certainly you could use kilograms instead, but the ratio is going to be the same, and therefore your answer is going to be the same. All right, so we're going to call this distance here x, from the center of the Earth to wherever this spot is where our ship is being pulled equally by the Earth and the sun. Okay. Now, by the way, you have a problem almost exactly like this in your problem set, but it's asking about the Earth and the moon. So, for instance, when we launched the Apollo missions from the Earth to the moon, they sped up, sped up, sped up. They turned their engines off, and then they coasted from the Earth to the moon for days. On their coasting, at first they were slowing down because they were still closer to the Earth. But at some point, their coasting began to speed up because the moon started pulling on them hard on the Earth. So it'll be a similar problem to this. All right, so we want the spot where the force of the sun on the craft is equal in magnitude to the force of the Earth on the craft. So that's G, mass of the sun, mass of the craft. If this is 1 and this is x, the distance from the center of the sun to the craft would be 1 minus x, and I got to square that, equals G, mass of the Earth, mass of the craft over, and that's just x squared. Okay. Now, obviously, some stuff cancels, which is kind of nice. The G cancels, and the mass of the ship does not matter. So it could be a little Matchbox car. It could be I don't know, a Tesla out in space. You know, there's a Tesla out there right now. It could be anything, and it's not going to matter. This location is set. Okay. Now, at this point, you could certainly FOIL this out, and you'd have a quadratic. However, we're going to cheat. Now, don't tell your math teacher this because they'll get really mad, but we're going to square root both sides. So you get the square root of the mass of the sun over 1 minus x equals the square root the mass of the Earth over x. Now, we're going to lose an answer when we do that, but the answer you're going to lose is the following. Let me explain. There is somewhere over here where the force on the Earth on the ship and the force of the sun on the ship are also equal. And you would actually get a negative value for x there, but we don't want that place. We don't care about it because the net force is not 0. I mean, yes, these are equal in magnitude, but they're not canceling each other out like they are here. So that's the answer you always lose here, so I'm not going to worry about it. And then if we cross multiply, you get, let's see, 1 minus root mass of the Earth times x equals root mass of the sun times x. And if you get x by itself, you're going to get, let's see, if you move this over to here, you're going to get 1 divided by root mass of the Earth plus root mass of the sun. For us, that's 1 over square root of 1, because we're calling the Earth 1, and then the sun is the square root of 330,000. And so you're going to get x, and it's going to be really small. I did work that out, but if you want to satisfy yourself, you should get the following in your calculator. Okay, and that's just AUs. Okay. Now, if you wanted to convert that to kilometers, you would multiply that. 1 AU is 150 million kilometers. So if you multiply that by 150 million, you get about 0.261 million kilometers. Okay. There you go. Now, if the ship were launching from here, you know, you get it going, you turn the engines off, it coasts. When it gets to this spot, it'll stop slowing down and it'll start speeding up toward the sun. Okay. Now, on the next video, I will talk about little g and the difference between the acceleration of gravity and the force of gravity. So I hope you found that video helpful, and thank you very much.